Okay, so let's start with compression factor, or capital Z. This is the ratio of the measured molar volume of a gas to the molar volume of an assumed ideal gas at the same temperature and pressure. So, compressibility factor or compression factor and molar volume are directly proportional to each other. Okay, so you can write it as uh, well, yeah, the ratio is expressed as a fraction. So molar volume of the gas and the molar volume of an assumed ideal gas, so that's gonna be in the denominator. And then since molar volume is V over N, coming from the ideal gas equation of state, that is equal to RT over P. So from there, not really transpose, but move the pressure to the numerator. So that's gonna be P times Vm over RT. Vm, or the V, and then there is an underline at the bottom. They're essentially the same thing. Okay? So yeah, this is also V sub m here is also the V measured. Okay? So at high pressure, so again, repulsive forces are dominant, no? So in this case, the compression factor is greater than 1. So notice, never mind. I don't think it's shown in the graph, but yeah, compressibility factor is greater than 1 for dominant repulsive forces. For dominant attractive forces, the compressibility factor is less than 1. So notice their differences. The molar volume measured is greater than the molar volume of the ideal gas. It's the opposite for attractive forces being dominant. If the gas is ideal, then it tells you that the compressibility factor approaches 1 and the pressure approaches 0. And the molar volume measured is equal to the molar volume of the ideal gas. Okay? Let's now move on to the virial equation of state. So this accounts for the small differences from an ideal gas using a series of powers of a variable. So there are two forms, no? Although I don't think you're going to need. I doubt that there's a distinction between the two. Um, by the paper, there are two forms, but essentially it's the same thing. So for Form 1, it is used when the molar volume is given, and you have to look for the compressibility factor. So essentially, the compressibility factor here is this entire thing, the one encompassed by the parenthesis. So we start first with, how do I say this? Mm. Coming from the ideal gas equation of state, PV equals nRT. Notice how it's similar, no, to the virial equation of state. PV equals RT, but instead of N, we have Z. So let's talk about the values inside this Z. So essentially A is 1, so supposedly A is here, but we can just write it as 1 since it doesn't have any other value, any other value except 1. So 1 plus B over Vm. B is the second virial coefficient and C is the third virial coefficient. Typically, it's only until B. As far as I know, the only gas that has a C or third virial coefficient is, I think, argon. Yes, it says here. Only argon has a virial coefficient C. That value is 1200 liters squared per mole, specifically. Everything else only has until second virial coefficient. And then we have the form 2. So When the molar volume is unknown, then you use this. So the B with the sorry, this is not an apostrophe. B prime rather. This is basically B over RT. In the same sense, C prime, C prime is C over RT. Don't forget the squared. Notice here from Form 1, the molar volume when it comes to C is raised to 2. So, yeah. So there's no more, sorry, sorry. There's no more fourth virial coefficient. We're only up to third at most. So, let's go here. By the way, it's important for you to memorize the virial equation of state. Most likely it won't be provided as well. So, how do you compare the density of solids, liquids, gases? So regarding density, the density of the gas is the smallest value out of all classical states. Consequently, the molar volume of the gas is the biggest significantly uh, compared to the other classical states. Let's look at this relationship. If we so we know that density is mass over volume, right? And molar volume is volume per mole. Mole here could be rewritten as mass over molar mass. And then uh, the hmm okay. So volume here becomes it's moved to the bottom of the mass in the denominator, and from there we know that density is mass over volume, so we transpose, not transpose, substitute rather. So molar mass over density equals molar volume. If we move the density to the left side, then that's going to be density times molar volume. Knowing that they multiply to each other, that means their relationship to each other is inversely proportional. So, yeah. Um, Regarding the reduced form of the virial equation of state, it's these two guys. So, P V molar equals RT times quantity 1 plus B over V molar. Okay? So, there's this concept called boil temperature. This is the temperature at which the second virial coefficient is equal to 0. And if that value is 0, then it tells you that the equation becomes the ideal gas equation of state. So this one. The boil temperature is the temperature at which a real gas behaves like an ideal gas over a significant range of pressures. So this is an example on uh, finding the boil temperature of a given gas. I wonder what gas this is. Yeah, I think it's air. Yeah. So there is a table um, of the second virial coefficients of various gases. In this case, it is air. And we actually tried to apply a linear regression here, although eventually didn't work, no? Since if you plot linear regression using the given values, this is from literature. So expect that it's given in the exam. You just have to know how to use them in forming a regression. So for temperature, we have 100 to 600 Kelvin, and then their corresponding second virial coefficients. So after placing these in the calculator, eventually you would find that the r squared is very far from 1. So 0.7 shows poor linearity. Change, you have to modify the settings such that instead of linear, quadratic is being applied. So this one, no. Then you identify the A, B, and C values, and as early as this point, you have to assign A as C in your calculator. Notice here, capital A equals negative 278.80, no? In your in the notation of your quadratic solver, when you press 5 equation, this is what you see. A plus bx plus cx squared. The small c here is supposed to be the capital A, in your quadratic regression. The b is the same, small b is the capital B here, and the small a here is the capital C in your regression. No? So, yeah, see how A and C are intentionally swapped. So after that, you just use the quadratic solver, and then you'd find x sub 1 and x sub 2 values. How do you choose which is the right answer? So, looking back at the given values, literature values, notice when the, the, the second virial coefficient came from negative to positive. So that's between 273 and 373 Kelvin, right? C, negative 13.5 to 3.4. That's when the signs changed. So the answer is most likely between 273 and 373 Kelvin. Now, how do we decide between these two values? What is between 273 and 373? X sub 2. So this is our boil temperature. We automatically exclude the value of x sub 1. So the more realistic answer is 327.75. As simple as that. That's how you solve this kind of problem whenever you're tasked to find the boil temperature. Okay, I'll skip this problem. Critical phenomena. I'll skip this part too. Let's now move on to the van der Waals equation of state. So we now account for attractive interactions. The repulsive interactions between molecules are taken into account by supposing that they cause the molecules to behave as small but impenetrable spheres. So this is the van der Waals equation of state. It could be provided in the exam, but personally, after solving the practice problems, I think eventually you'd be memorizing this already anyways. So you just have to be careful. P is equal to nRT over V minus NB minus AN squared over V squared. If you want to express this in terms of molar volume, then it's going to be RT over V molar minus B minus A over V molar squared. Okay, so A and B, A is the strength of the attractive interactions between the molecules and the constant, and the B, that means repulsive interactions between the molecules. One is for repulsive, one is for attractive. Both of these are van der Waals coefficients, and there is a corresponding table for that. So for ideal gas, according to the kinetic molecular theory, individual volumes of molecules are negligible, right? In the case of real gases, the non-zero volume of the molecules implies that instead of moving in a volume, they are restricted to a smaller volume. So this is expressed as V minus NB in the formula, where NB is approximately the total volume taken up by the molecules themselves. So recall these conversions. These are going to be important. 1 centimeter cube is 1 milliliter. 1 decimeter cube is 1 liter. Although this isn't exactly accurate, there is a small discrepancy. No? Yeah, we are doing this for approximation only. And yes, the A and B values for every gas as mentioned earlier, there's a corresponding table for that. List of A and B values for corresponding molecules. Specifically for CO2 gas, uh, A is 3.610 atmosphere liters squared per mole squared. For B, the B value is 4.29 times 10 to the negative 2 decimeter cube per mole. Again, we can interchange decimeter cube and liter. They're essentially the same value. Okay? And as far as I remember from my encounter in the exams, the units, this is uh, this is the default unit, no? But you could be given the A and B values in terms of different units, and I suggest that you convert them into uh, atmosphere liter per mole or liter per mole, because it might be confusing, no? Although that's just personally what I understood from my experience. Could be different from yours, but as much as possible, try to simplify with the units. Just stick with one, okay? Okay, so regarding the features of the van der Waals equation of state, first, perfect gas isotherms are achieved at high temperature and high molar volume. So, yeah, given high temperature and high molar volume, gases would behave like ideal gas. How? So it's shown here, no? Um, if the molar volume is really high, then the molar volume minus B essentially just becomes molar volume. So for example, 300 minus 0.001. So we have 299.999. And the A over molar volume squared, that essentially becomes 0 because of how big the molar volume is, no? And it's in the denominator. It makes the fraction almost equal to 0. So from there, what do you observe? It This formula essentially becomes nRT over V molar. So it kind of like looks like the ideal gas equation of state already, no? Okay, second feature, liquids and gases coexist when the attractive and repulsive forces are in balance. Third feature, the critical constants are related to the van der Waals coefficients. So, aside from having the specific values of A and B for each kind of gas, there is actually a formula, no? Specifically for van der Waals equation of state, the formulas for A and B are as follows, no? So, yeah, these are practice problems for uh, finding boil temperature, finding the molar volume, estimating it using a certain equation of state. So here we have two other equation of states, no? Equations of state rather. Berthelot and Dioterizzi. So don't worry, they will uh, actually in our case we were told that they won't be provided in the exam, but they were. I think that's what I recall, although I might be wrong. Okay, same idea. It's just that the formulas are different. So we estimate boil temperature. Oh wait. This is another way to find boil temperature. Instead of our usual estimation, uh, this is more specific. If we are given a function, and uh, what exactly do we use, or do we do rather, with the function? we have the A and B values as well as the C. Um, we substitute basically. I think that's it. Yeah, as simple as that. We're given the A, B, and C values, and we have this function. Substitute, plug and play, find the boil temperature. That turns out to be 501.02. I tried to compare, tried to answer this alternatively using the estimation method. Um, so we know that this is methane, no, CH4. We find its corresponding temperature and second virial coefficient values from literature table and plot them. Uh, so quadratic regression, and then it turns out to be 477.83 Kelvin. So as you can see, it technically is between 373 and 600, where you see here, that's where the second virial coefficient became from negative to positive. So notice how they are quite far from each other, 501 and 477. As I said, this is an estimation only. But technically 501 still falls between 373 and 600. And since we're given a function, again, this is more accurate. So, yeah. Next. Example 28. We are still technically doing the same thing. Estimate boil temperature. That's honestly, I think, one of the most fun kinds of problems in this subject. Once you understand how it's solved, then it's easy from there on. This is one method. It's confusing, although I think I remember coming up with a different method that's much simpler. But yeah, this is one solution. Uh, Concepts such as excluded volume are involved. So yeah. So here we have the phase diagram, plot of pressure and temperature, solid, liquid, and then vapor. Eventually, we have this something called critical point. No, this is the point where the liquid vapor phase boundary ends, making liquid and gas phases indistinguishable. So this kind of phase is supercritical fluid. For the triple point, as you can see here, this is the point in a phase in which three phases coexist: solid, liquid, and vapor. Okay, we're almost done. Just a little more. I don't think I'm going to cover viscosity anymore. hmm We will stop here. I'll resume later on. We're gonna then talk about the principle of corresponding states. Okay, bye bye.